Imagine a freezing rail yard in the dead of night. The temperature has plummeted well below zero, and a thick layer of frost covers the steel tracks. In the distance, a massive shadow looms. It is a heavy-haul diesel locomotive, standing perfectly still. But despite the fact that it hasn't moved for hours, the ground vibrates with a low rhythmic thumping. A steady plume of white exhaust rises into the crisp night air. It seems like a massive waste of resources. Why would a multi-million-dollar machine, built for efficiency, be left running for hours on end while it has nowhere to go? The central mystery of diesel locomotive idling often confuses people who are used to simply turning their car key and walking away. How much fuel is this giant engine actually burning while it sits there? Why don't the engineers just shut it down and restart it when the next crew arrives? Most importantly, what would happen if someone actually decided to turn it off in the middle of a brutal winter storm? We are going to explore the high-stakes world of railroad winter operations and discover why one seemingly sensible decision to save fuel could lead to a catastrophic engine failure or leave a massive train completely disabled. To understand this properly, we first need to correct a very common misconception. You might see a locomotive idling and assume that every single train engine in the world stays running throughout the entire winter season. That actually isn't the case. The decision to keep an engine idling is a calculated choice that depends on several critical factors, including the age of the locomotive, its specific mechanical design, the severity of the outside temperature, and whether the yard is equipped with external heating systems. Railroad operating procedures are incredibly strict, and modern locomotives are actually much smarter than their predecessors. Many locomotives built in the last 20 years feature advanced computers that can shut the engine down automatically to save fuel, only restarting it when the internal temperature drops too low or the battery charge begins to fade. However, there is a legendary secret in the rail industry that most people outside the yard don't know. The diesel fuel itself is actually not the most vulnerable liquid inside the locomotive during a cold snap. The primary reason these massive machines keep running is found inside the cooling system. This is the biggest reveal of the locomotive world. Unlike your car, which uses a mixture of water and glycol-based antifreeze, many traditional locomotive engines have historically relied on pure water for cooling. There are engineering reasons for this, as water is exceptionally efficient at transferring heat away from the massive engine block during high-load operations. However, as any middle school science student knows, water expands when it freezes. If a locomotive engine is shut down in extreme cold, the cooling system immediately begins to lose its residual heat. Once that water begins to freeze inside the intricate network of pipes, radiators, and engine passages, the resulting expansion can literally crack the engine block or burst the radiator cores. The EPA actually identifies coolant freezing and subsequent engine damage as one of the primary reasons why older locomotives must remain idling in cold weather. Instead of a simple restart in the morning, a crew might find a locomotive that requires hundreds of thousands of dollars in major repairs because the vanes of the engine have literally exploded from the inside out. But even if the coolant is somehow protected, the locomotive still faces another formidable winter enemy: the sheer physics of its own size. Restarting a giant diesel engine is nothing like starting a sedan. We are talking about a prime mover with 16 cylinders, each one larger than a gallon bucket. When the temperature drops, the lubricating oil inside this massive engine becomes thick and resistant to movement, turning into something more like molasses than oil. On top of that, the massive battery banks used to turn the starter motors lose a significant portion of their performance in low temperatures. The starting equipment must find the strength to turn over thousands of pounds of cold metal components against the resistance of that thick oil, If a locomotive fails to restart in a remote yard, it can delay an entire train, blocking a main line and throwing off the logistics of a whole region. Avoiding these cold start problems is often considered more important than the cost of a few gallons of fuel. The engine isn't just there to move the wheels, though. This brings us to the third critical reason, the air brake system. Trains rely heavily on compressed air to function. The locomotive's air compressor, which is driven by the engine, supplies the entire length of the train with the pressure needed to operate the braking system and other pneumatic components. When a locomotive is shut down, air pressure can gradually leak out of the system. In the cold, seals can stiffen and leaks can become more prominent. If the pressure falls too low, the train is essentially a dead weight that cannot be safely moved. The locomotive may need to run just to maintain the main reservoir pressure, ensuring that the brakes are ready the moment the crew steps into the cab. Federal regulations recognize the need to maintain this air pressure for safety as a legitimate reason for long-duration idling. Without a steady supply of compressed air, a train is simply not a safe vehicle to operate. You must see the locomotive as a mobile power station. The engine performs vital tasks even when not pulling 20,000 tons of freight. It keeps the complicated control device's batteries charged and warms the cab for the following crew. Screens and sensitive relays can fail if electronics get too cold. The locomotive supplies head-end power for passenger car lighting, climate control, and food service. A stopped locomotive may appear idle, yet it works hard to keep its heart beating and systems ready for use. You might question why railroads don't install a modest heater instead of using a 3,000 horsepower engine to stay warm. That brings up the cost. Railroads dislike idleness. It drains their profits greatly. Idling locomotives burn 3 to 5 liters of diesel fuel every hour. Spread that across thousands of locomotives over a long winter, and the expense is astronomical. Idling wastes gasoline and produces exhaust pollutants and noise that can annoy rail yard neighbors. It adds unnecessary engine hours, resulting in more frequent and costly maintenance. Because reducing idle emissions is an important environmental aim, the EPA has issued particular recommendations urging rail facilities to employ innovative technologies. Idling may keep the locomotive warm, but it's not free or desired for railroad accountants. This trade-off between protection and expense led to the contemporary automatic engine stop-start system, AESS. This technology transformed railway winter operations. Sensors in AESS monitor the locomotive's vital indicators. The mechanism can safely shut down the engine to save fuel when the train is parked. But the computer stays awake. It monitors battery voltage, cooling water temperature, and ambient air temperature. AESS automatically restarts the engine if the water temperature dips below freezing, or the battery charge decreases below a specified level. It operates until the systems are warmed and the batteries are full, then shuts down. Some railroads utilize small fuel-efficient diesel engines called auxiliary power units to warm the main engine and charge the batteries without running the huge prime mover. Other yards employ shore power, plugging the locomotive into a ground outlet to run its heaters. Despite these technical advances, many locomotives idle. It may be due to outdated equipment without updated systems. Sometimes temperatures are so dangerously low that the AESS would restart the engine every 10 minutes anyhow, making it more efficient to let it run. In other circumstances, heating equipment may be failing or the operational risk of a botched start outweighs fuel savings. A dispatcher's worst nightmare is having a train set to go and discovering the lead locomotive has a cold block that won't turn. Always a risk management choice. To avert a multi-thousand-dollar calamity, the railway is buying a few gallons of diesel immediately. Given what occurs if a crew does it wrong, this decision pays dividends. Imagine a locomotive shut down in a polar vortex without protection. Block interior temperature drops within hours. Cold weakens batteries, which lose chemical energy. The liquids thicken. Lack of antifreeze causes cooling water to crystallize and expand. When the crew arrives, the locomotive is frozen and lifeless. The radiators may be broken or the seals destroyed. They may spend hours using specialized equipment to jump-start the big engine even if the block is intact. The cost of downtime, repairs, and missed delivery dates can be staggering. A locomotive sitting still in winter may look like a lazy giant, but it is typically balanced. It preserves heat, air pressure, and electricity for its work. In a hostile environment, only idling keeps a machine alive, whether it's a vintage engine's hum or a new high-tech unit's automated cycle. The next time you see a rail engine billowing smoke in a freezing yard, remember that it's fighting thermodynamics to keep goods moving. A locomotive that never sleeps is road ready.